Alright, back again. Our first question in chapter 4 is, a hydrogen atom with the Bohr radius of a half an angstrom is situated between two metal plates 1 millimeter apart, which are connected to opposite terminals of a 500-volt battery. What fraction of the atomic radius does the separation distance d amount to, roughly? Estimate the voltage you would need with this apparatus to ionize the atom. What we know for this problem is the atomic polarizability of hydrogen is equal to 0.667 times 10 to the negative 30 meters cubed. This is found from a table in the book. Also, we know that the induced dipole P is equal to alpha, the atomic polarizability, times the E field. For the solution, we need to remember that the goal is to find the ratio of the separation distance to the atomic radius, which we see below. Note that the radius is half an angstrom, which was given, which is equal to 0.5 times 10 to the negative 10 meters. To find the separation distance, consider the dipole moment from the polarization. P is equal to alpha E, which is also equal to ED, where E is an electron, which comes from hydrogen, which only has one electron, and D is the separation distance. Note that we solve algebraically for D, and we get alpha E over E, where alpha is the atomic polarizability. For the atomic polarizability, let's recall that in the book, they label it as alpha over 4 pi epsilon naught in the units of 10 to the negative 30 meter cubed. So what we'll have to do is a little bit of manipulation here with the given information. As you see, we simply solve for alpha and plug in the constants and boil it down. Let's be careful to note that the units are going to be critically important here, so for all these simplifications, I will include the units in their cancellations. The next part of the equation for separation distance that we don't know yet is the electric field. We do know, however, that we were given a voltage and a plate separation. With those two things, we can find the electric field by dividing the voltage by the plate separation, and we get the value seen here. Now that we have all the parameters established, let's go ahead and plug those into the separation distance equation and simplify. Note that we are dividing by the charge of an electron here, and we see that the units start to cancel out as such. One round of simplification leaves you with coulomb volts per Newton, which is not exactly what we need. But we know that a volt is a joule per coulomb, so we can cancel the coulombs in the numerator there, leaving you with joule per Newton. But we know that a joule is a Newton meter, which cancels the newtons, and we're left with the desired unit of meters. Now that we have a Bohr radius in meters and a separation distance in meters, we can find the ratio. The ratio turns out to have a magnitude of 4.6 times 10 to the negative 6, aka really small. To find the voltage needed for the ionization to occur, we'll need to note that the separation distance must equal the Bohr radius in order to ionize. So what we'll have to do is substitute that Bohr radius back into the separation distance equation and solve for V, knowing that E is equal to V over X. Once we find V, then we can substitute in the parameters of R, E, X, and alpha. Again, be careful with the units because the units are going to jumble up, but we end up getting a Newton meter per coulomb, which is a joule per coulomb, which is a volt, which is exactly what is needed.